having developed a framework for L1 union L2, L1 intersection L2, L1 minus L2, of course L2 minus L1 as well, let's spend some time on this framework and analyze a couple of interesting things. The first one to observe that this construction is indeed correct. The reason is when you take an arbitrary string x and you wish to know whether it is accepted by this, or precisely whether x is part of L1 union L2, and all that we will be doing starting from P, we start parsing x with respect to this automaton. Similarly, starting from A, we start parsing x with respect to this automaton. If at least one of them stops at a final state, we say it is accepted. So one can independently run on this and run on this, finally take a call whether to accept x or reject x. Similarly, to talk about L1 intersection L2, first simulate on this, see whether it reaches a final state, and then simulate on this, see whether it reaches a final state. But the fundamental question is, can we come up with an automaton which will do this unified operation? The automaton itself will tell you that it is part of L1 intersection L2, because that's the purpose, right? We want a mission. We want a mission which will do L1 union L2, L1 intersection L2, given L1 and L2. Answer is yes. And when we start parsing starting from P or starting from A, and the same thing can be visualized as starting from PA. Starting from PA, you start parsing x, and whenever we see a symbol, and with respect to the first transition table, see where we will move to. Similarly, with respect to the second table, see where we will move to. And so ultimately we will be working in the space of cross product, and as we parse one symbol after another symbol. Correct? So now, keeping this in mind, we have explored this strategy and designed a mission. With that, we identified in case we want to accept L1 union L2, and set of final states should be such that at least one of the final states should be present in the automaton, or in the set of final state corresponding to L1 union L2. If it is L1 intersection L2, then both must be present, therefore it is RA and RB. But some states in this automaton, some states are not reachable starting from the start state. So such states can be pruned. For example, starting from PA, we always start from this state, right? So on reading a we move here, and on reading a B, we continue to stay at PA. But this one does not have any incoming arc, so which means starting from this cannot be reached. Similarly, this state does not have any incoming arc, so starting from PA, the state RB cannot be reached. Similarly, this state, it cannot be reached. And can this be reached? Starting from this, I can reach QB and then reach this. Can this be reached? Yes, this can be reached, therefore this can be reached. And this can be reached, therefore this can be reached. And how about this? Via this you can reach. So what I'll do, let me redraw this by removing these three. So now after pruning those three states, so we have this. So this clearly accepts L1 intersection L2. As you can see that starting from here, when we come over here, it ends with the pattern AB, and it does not contain AA as a substring. And after coming to this state, you want to read an A here, so which means you can come back with AB again, or you read a B, which means you have lost the pattern, you have to go back and start reading AB again. But at this point in time, you start reading one more A, then you see that you read AA, but AA should not be accepted. So the moment you go to this part of the automaton, you can't come back to this, and anything that has AA in it, you will be somewhere here, one of these three states, and all are non-final states. Therefore, the string will be rejected by the automaton. So now you may ask, is this the simplified automaton for L1 intersection L2? For example, can I simplify this further? Or rather, is this a minimum state automaton for L1 intersection L2? And this has got 6 states. Can we think of an automaton having less than 6 states? Okay. Observe this. The moment you read second A, you reach this part of the automaton. So now one can stay here and continue to read both A and B. Correct? And it will still be rejected by the automaton. So these two states are redundant, or rather, out of these three, we can have just one state, and the other two can be pruned. So the message is, this framework gives you a deterministic finite automaton for L1 intersection L2 if these two are deterministic in nature. If L1 and L2 are deterministic finite automaton, then the framework also gives you a deterministic finite automaton for L1 intersection L2, but the automaton we obtain need not be a minimum one. For example, this one has got 6 states, but this can be pruned further. And similarly, the framework gave a couple of states which are not reachable from the start state. So first we have pruned those 3. We can prune some more as well. So the simplest string that satisfying both is AB. So we read A and B, except, and to start with, one can have any number of B's, and when we are at this place, we read a B. Where should we go to? Because we lose that pattern, we don't remember, so we need to read the pattern again. When we read A, we can come back here so that we still end with AB. Okay, so with respect to this, AB is defined, with respect to this, AB is defined, with respect to this, B is defined, but A is not. But when we read A, it will have AA in it, but it should not have AA in it. So when we read A, we go to a state, and now with respect to this state, if we read A comma B, we stay here. Which means we obtain a 4-state automaton accepting the language L1 intersection L2, which is minimum because we need 3 states for this and 1 state for this. So anything less than this is not possible. So now a framework like this works. However, it may have some redundant states which are not reachable from the start state, and it may not give you minimum, and it will certainly give you deterministic mission if these two are deterministic. Okay, if one of them is non-deterministic, so you will also obtain a non-deterministic mission here. Okay, so now what happens? Can one spend time on this and then fine tune to obtain minimum? Answer is yes. That's precisely what we have done. And so this will come handy when, just by looking at L1 and L2, for some questions it may be difficult to construct L1 intersection L2 or L1 union L2 directly. And but independently one can construct L1 and L2. So for such questions, this framework will be of use. That's one part. On the other side, L1 is a set, L2 is a set, accepting set of strings over an alphabet. Now it is natural to ask, can we apply some set theoretic operations like union, intersection and set minus, and talk about new languages that one can obtain from the given two sets, namely L1 and L2. So that's precisely what we have done. So it need not give you minimum, and but it certainly gives you an automaton which precisely answers what we want, be it L1 union L2 or intersection or set minus. And so all this is helping you to design a mission from many perspectives. So having seen couple of missions, and some of them perform pattern, some of them perform counting, and let's explore some more varieties. And the other interesting question is, given a deterministic finite automaton, how do we obtain a minimum one? Given a non-deterministic mission, how do we obtain an equivalent deterministic mission? So all that we shall explore in due course.